Okay.
Oh, yeah, I can.
Yeah. Okay. So
Sure.
I leave you the full management of the session.
Right. Thanks a
Okay.
lot.
Thanks to you. Bye-bye.
Bye.
Bye.
Okay, so we're not too late. Just 1 minute late. That's good. So hello everyone. It's good to start again with the trade session. So we're going to try to keep. I mean, I don't know if the lecture is going to be every couple of weeks, but what we should stick with is to have 2 students presenting every 2 weeks in any case. So we will keep at least the first half an hour every 2 weeks, if that's okay with everybody. I mean, if there's no issue with this, and then every now and then you'll have a lecture as well. That's going to be yeah, it's going to be for this year. I mean, today Giulio will present, but first we have so I can't remember who's on. Katerina, I think, is it? Yep, that's Katerina, and then Jarod. So Katerina, you can start. You can share your slides. I believe we can't hear you so much.
Now you can hear me.
Yeah, it's not very strong, so you will need to speak a bit louder if possible, or get closer to the mic.
Okay.
So yeah, we can see the slides.
Okay. My title of the project was Modeling Synthetic Catalog of Earthquake Ruptures in Complex Interacting Fault Systems. As you can see here, that is what we have done so far. We started with 7 simple faults, normal fault with same deep angles, with same properties, just different in the size and with the same direction. These are the results of that models that were shown in my recent 2 posters in Corfu and in Netherlands. In these first results, we compared two tectonically active regions, low and moderate, moderate with a slip rate of 1 millimeter per year and low with 0.1 millimeter per year, and with 2 different dynamic coefficient of friction. As we expected, when we decrease the dynamic coefficient of friction, the number of the earthquakes decreased, and also the magnitude of the earthquakes decreased. And in that posters, we compared the magnitude frequency and the average slip of the results of these 4 different models. These were the baseline of the initial part of our main project, which is modeling central Apennines. Based on a Faltusha database, we started modeling the whole central Apennines. Faltusha gives a good detail of the trace of the faults, good trace of the faults. We started with 2 faults, Montevettore and Laga, as we can see here. This is a 3D model of the faults generated with these characteristics, slip rate 1.2 for Montevettore and 1 millimeter per year for Laga, with 2 different deep angle, but both southwest deep direction. To better see the models, I will show you 3D of them. To compare the interaction of the results with the individual, we run 3 different models. First, Montevettore, Laga separately, and then both together. As you can see in the left picture, it's the catalog generated for Montevettore. middle Laga and the right both interaction. As we can see that in Laga, the minimum magnitude increased to 2.8, and it's more likely because the mesh size increased in Laga fault because of the size of the faults in comparison with Montevettore. And the interacted catalog is mostly follow the pattern of Montevettore, which is the biggest fault in this model. Then we compare frequency magnitude diagram of these three models, as we can see here. To better see them, I put it in the same diagram. You can see there is no considerable difference between the three models, but as it is more clear here, the interacted model follows Montevettore faults, especially in larger magnitudes. You can see here. Again, we compared the average sleep versus magnitude in these three models. And let's see in the next slide. Also, I put them all together in one diagram. You can see that also have the same pattern and mostly follows Montevettore, that is the largest fault in these models. To see the rupture in the surface of the fault, I will play this video for you to see what happened inside the rupture duration. As you can see, very small, it starts with very small ruptures. Then when it has the large enough stress during in the surface, the large rupture happened and a large earthquake happened in the model. So you can see here, sometimes they are transferred from one fault to another. Then the next phase of our model is modeling the whole central Apennines. Now we started modeling this part with 7 faults in central Apennines: Montevettore, Laga, Norcia, Monte Albano, Capitiano, San Giovanni, and Lungamani. This is the model generated, the 3D one with these properties that are actually extracted from the literature that has been written. Also a 3D model of the faults to see better what is happening in this model. The result of this model will be shown in next few days in GNGTS in Bologna to see the results of this model. And that's it.
Okay, thank you, Katyri. So time for questions. Well, I have several, but then maybe you know, I could be I could give the mic to somebody else. Manandrin.
Hi, looks really cool. I missed the beginning, unfortunately. Maybe you said about what in these models, what starts and stops the quakes? What's the starting and stopping criteria?
Could you please repeat the question?
So you showed the seismicity sequences with different magnitudes, and in these models, what determines when a quake happens somewhere, and what determines the magnitude?
Actually, the strength of the fault, I think, that decides where the first rupture happens. The model starts to give pressure to all the faults. Then one part of the fault, when it starts to fail, the rupture will happen. Then it can be transferred to other part of the faults or to the next faults, the faults that is next to these faults, if I'm not mistaken.
But so is it, do you model a rupture propagation, or is it just like a randomly drawn source size?
That's rupture propagation actually happens. For example, in one part of the fault, for example, yields at this specific stress rate, then starts to propagate to other part of the faults and change the stress and friction in other part of the faults.
Cool, thanks.
Okay. Rachel.
Hi. So I was wondering, you showed the video of the different nucleations at different points. What was the time scales of that video?
The years that is passing, this is during the 500 year of, as you can see, you cannot see here, but it's during the years actually. This video that is 1 minute is for 500 years duration of the observing the catalog. The whole catalog is for 50,000 years, but the video is just 500 years of you can see here that this is the year 38,000 years.
And so you start off by defining your stress fields, and do you define anything specific on fault, like maybe the R parameters or friction parameters? How do you go about that?
The friction parameters were defined, static and dynamic coefficient of frictions were defined for the surface of the fault.
Okay. Giulio, you have a question. And then, yeah.
Okay. I think Aurora should come first. I make my question is very simple, Katare. Thank you so much for your summary, the summary of the work you did. How do you decide what are the constraints for the geometry, the roughness you gave?
The roughness is randomly generated on the surface of the fault by MCQC. So I cannot that much control the roughness of the surface. It's randomly assigned by the MCQC.
Good.
Hey, I just lowered my hand because Giulio just asked
Right.
the same question. Yeah, because I saw that the 3D models in terms of geometry looked very complex, and I was wondering how was it possible to make such detailed models of the faults you are considering. That's it.
I have two quick questions, maybe, Katere. The first one is that there seems to be an initial loading phase. Is that right? I mean, it seems that the magnitude at the beginning of your simulations are somewhat lower. So you need some time to reach. Okay, so you're basically loading the model.
Yeah.
Right?
The first part that you can see that the magnitude of the earthquake are smaller when it goes, it's increased the number and the magnitude of the earthquake because actually it started loading. Then it arrived at a certain amount of stress, then it starts to yield the surface of the fault. Because of that, we are planning to cut the first, for example, 2,000 year of the catalog to consider more actually normal catalog than the.
Good. And the second one is, it seems to be that you have two branches when you look at the slip versus magnitude. So what does explain, the fact that you have two branches? Yeah.
This one.
Yeah.
Yeah, right. This is also the question that we should ask Olaf about it. I don't know, maybe it's the problem of the MCQC because it happens in all the models that we generate. For example, in the one that we shows in previous conferences that has the same problem. There is a gap in between. This is the problem of the model that we should be solved.
Okay, it's nothing, related to I don't know, the fault geometry, or is just something that you're not sure what's causing this at the moment. Is that right?
Actually, no, I'm not sure what is causing that problem.
Okay.
Could be linked to the meshing also. Depends on the meshing on.
All right. Okay. I mean, and compared to normal
Estimate.
scaling, I mean, because we know, I mean, what are, the expected scaling law between, sleep and magnitude. So,
Yeah.
so I guess, the two branches show two very different stress drop, if I'm correct. So, yeah. Did you try to compute the stress drop, average stress drop?
No.
Okay.
Yeah, could be it's a good idea. Yeah, we have to work on that to understand why.
Yeah.
We discussed this morning because it's quite strange. This.
Yeah. Menandrin, you raised your hand again.
Yes, first I have a comment on this discussion. That it could be interesting to look at the aspect ratios of all these ruptures that could, lead to different stress drops and two different paths.
This one, you mean?
Yeah. Maybe just, look at the distribution of length to width ratios of the individual ruptures, and also as a function of magnitude. And this is something that we can measure for real quakes as well. So,
Because your
be an interesting
intuition, Menandrin, is that it might be related to the aspect ratio.
could be, yeah. That I don't know that. I don't know how the model works in detail, but
Yeah.
that the ones with more slip per magnitude
You mean the
could be some with anomalous aspect ratios. They're particularly long compared to the width, for example.
Okay, so all right. Yeah, possibly. I don't know. Okay, so
And also the question is maybe related, that the maximum magnitude that you have is about 6.6 or something, which is, about the maximum observed earthquake with Norcia, which was about 6.5. Is there a chance in these simulations that the faults would link up and rupture in one go in something that is bigger?
you mean what do you mean by the
Yeah, in this figure, so the one with the magnitude versus time.
yes.
You have a pretty clear upper maximum of 6.6, and I guess this is when your largest fault ruptures fully.
Yes.
And I wonder if you could get, multiple of these segments in the Norcia, so Amatrice, Norcia, and Viso. It's actually kind of surprising that, Norcia was almost but not quite ready to go when Amatrice ruptured. It had some very strong shaking, and you have this fault that's ready to produce a magnitude 6.5 quake, but it's not quite ready, so it doesn't go quite. It goes 3 months later. And I wonder what the conditions are and the possibility in these type of models that you can actually, trigger a cascade of faults.
Actually, I think the main thing that we have to observe is that the interaction that you mentioned, for example, to see if it's possible to happen that the all surface of the faults near each other could fail or not. In the video that I showed, that it doesn't happen, that the two faults at the same time try to rupture totally, but some part of the Laga and some part of the Montevettore near to each other sometimes happens that rupture, and that generates a large magnitude earthquake. So if we model the whole central Apennines or the faults you mentioned, Norcia or other faults, we can see that even if the distance between the faults can control this, that maybe large earthquake with the rupture with the whole surface of the fault happened or not.
Okay. Yeah.
No, just to add that, yes, the idea on this project is exactly to try to force in some way this cascade earthquakes. So we want to understand if not only if it's possible but to force in some way the model to be possible, to understand what's happened when we have this kind of interaction. So we were waiting for this also here, but maybe are only two faults and maybe not so close as is needed by the model. So we want to change something, adding faults, but change some parameters to force in some way this this kind of interaction, to understand what's happening, then what's happening in the catalogs when we have this kind of interaction.
That's great.
I see more questions. So Marco.
It's very fast. I was wondering, Bruno, in light of what you were saying, if you are planning to perform, for example, a sensitivity analysis in order to understand, depending on the relative position of, say, two faults and their geometries, the extent to which they are interacting and therefore generating joint ruptures.
Yes, absolutely. Yes, we have to understand which parameter we can explore and which one we can take. No, we have not to move, not to change. So yes, the answer is yes. So we have to understand which are the parameter more influencing the interaction.
Okay.
I don't know if Katere want to add something.
No, just
You answered well. So maybe a last question by you, Giulio.
Yeah, I think I discussed this with Bruno some time ago. Of course, you have a fault here, but then actually we have fault zones. And a lot of macroseismicity or the small seismicity is not in the main along the main fault, perhaps. So this is one thing to consider. And then the second one is, of course, the network of faults you have in this area of the Apennines, because there are also trust. I mean, there is the Sibillini trust, another connection between the faults. So the rupture travels for a while on one segment and as another pathway. So I don't know if adding at least one linkage of some kind, because there are probably, but outside there. So, but this adds complexity, and already like this is quite difficult. So I don't know. It's just thinking about that.
Yeah, what can I say is that yes, it's very complicated to have an idea of the 3D geometry. And I worked a lot reading all the papers we have to try to understand something, but we have really no strong ideas how is really in depth. So the idea, my idea, but then it's the PhD of Katere can change a bit. My idea is to try to simplify in some way something that is not simple but is complex, to understand which parameter can change exactly with some sensitivity test the interaction, and so in terms of expected seismicity and so in seismic hazard, not thinking to have the final good model for central Italy, because maybe it's more complex what we have to model, but to understand if this kind of approach, from this kind of approach, we can learn something more about the possibility to use this kind of approach when we have information really in depth. Because the problem, yes, we have we know that we are putting only 2D faults, is 3D, but we are not considering all the volume. We are not considering the trust. We are not considering the fault, not the smaller fault. So it's more complex, we know, but we have no idea how to really construct in depth the geometries, and then the uncertainties can really be too large to be managed. That's my idea, but any idea is welcome for sure to improve this approach.
Yeah, what we can infer from seismicity in that region is really it's a terribly complex fault network. One thing that might be useful for you is from in the Waldhauser et al. Paper, they have done some clustering of seismicity and come up with a very simplified discrete fault network. I don't know if you were aware of this, but that's just some planes that you could look at to compare to the representation that you have at the moment.
You mean the vettore area?
No, for
Pardon?
the yeah, for Montefiore, let's see if
Yeah.
the Waldhauser paper, yeah. Maybe we should move on because we're going to be very late otherwise. Thanks a lot, Katia, in any case. Jarod, sorry.
Yeah, okay. Can you hear me?
Yes, we can.
Okay,
Go
perfect.
ahead.
I will share my screen. Oops, okay. So can you see my slide here? Okay, so I will probably first start with the result of the first year of the PhD. So what I did exactly is to create some stochastic rupture pattern from the area sources that I'm mentioning for like a couple of time right now. So as you probably remember is that when I was generating the stochastic rupture pattern, at the end we had a really huge aleatory variability, as you can see here with the hazard curve for each rupture pattern. And on the right side, you can see directly the 16 and the 84 percentile of all the realization that I made for Stockholm and L'Aquila. And the distributed seismicity, yes, does not reflect the spatial distribution of earthquake. And of course, we want to create a better model that allows us to better represent our geological understanding of the spatial distribution of earthquake. And for that, we want to see if this is possible actually to reduce this aleatory variability. And there is in distributed seismicity different sources, different model that we can use. So there is the area sources with an homogeneous occurrence rate over the whole area. And what we can use also is the fault source model. So we know that there is some fault in some areas, and for those faults, we will set different parameters such as the magnitude frequency distribution or the geometry or all these kind of things. And what people do actually to compute these hazards is to add to this model, to this source fault model with a smoothed seismicity model. So the smoothed seismicity model in this case is here to capture the variability in the space and time distribution of past and future earthquake. And so as you can see on the right, instead of having some area sources like in the left with homogeneous occurrence rate over all this area, for example, in this case you will have for each point here, I said it's for French, so this is the European seismic hazard model of 2020. So for each dot that you will have here, you will have a different magnitude frequency distribution, so different occurrence rate, so spatial. So the occurrence rate will be heterogeneous over the area. And with that, as I said, you can couple the fault sources, and our point here is instead okay, in the first place we did our simulation on the area sources, and the aleatory variability was very huge. And if now we do exactly the same as we did for the area sources, but for fault sources and smoothed seismicity, what we will end up at the end, what we think we will have is a lower variability. It means that if we have a lower aleatory variability, that we can improve that we can improve our modeling. So I did the computation for both, so for fault sources and for smoothed seismicity sources. And I don't know if you remember, but firstly, what we need to have is, because we are sampling the occurrence rate, we are sampling the occurrence rate from the fault sources and from the smoothness seismicity. At the end, if you are generating a lot of simulation of a sample like this, what you will have is, if you compute the hazard curve for a lot of simulation, yes, if you retrieve the mean hazard, you should retrieve the mean hazard curve of the one that you have when you are considering the full model. It means that, let's say that for 50 years, I will have, I don't know, 20 ruptures. If I try to compute, if I do a lot of simulation of 50 years, I will try to retrieve at the end, if I mean all this simulation, if I mean the hazard curve, I should have exactly the one from this model. So so for now, what I'm trying to see is if the aleatory variability is lower than for area sources, but I still not have exactly the same mean hazard curve. So before looking at the variability, I still need to fix the code. So I still have a couple of problems, and I think I found it, but I don't want to go in detail right now. So to see if I have some problems, what I did basically is the discrepancy between the mean hazard curve that is computed using the European Seismic Hazard Model of 2020, so the red curve, and with my simulation are not fitting well. And it is coming from the fact that I have some problem when I try to compute when I'm trying to do the simulation for only the fault sources model. So the smoothness seismicity model is working well. So the two mean curves are fitting perfectly, but not for the fault source model. So for each fault sources, I try to generate a stochastic event set. So over a lot of years. So in this case, it was for 50 years investigation time. So I did 1,000 simulation for 50 years. So and I look at how many occurrence rate that I have in all this simulation. And what you can see is, so the black curve is the original magnitude frequency distribution set for these fault sources. And when I try to see if in 1,000 of simulation I have exactly the same magnitude frequency, so the same MFD, I end up for these fault sources not having exactly the same MFD. So it means that in my model, actually, I'm not reflecting exactly the same occurrence rate for the fault. So there is something wrong in what I did. So I need still to figure out what it is. And also, what I was looking for what I want to do exactly now is well, I did that in parallel actually. So now, as you probably know, in area sources, the ruptures are totally homogeneous. It means that for the biggest magnitude, such as magnitude 8, let's say, they have exactly the same occurrence over all the area. So, and we think that this is not probably correct, and we think that the magnitude like 8 should be constrained in probably in a couple of localizations, it cannot happen in all the area. So what we want to do is to create a pattern which we align with what we think is geologically possible. It means that, let's say now that we have only two possibilities, two localization where the highest magnitude can occur. We know that this fault, which have the possibility of generating a magnitude 8, will have an impact on the seismicity around the fault. Let's say that, for example, the magnitude 8 is in a certain direction, and let's say with a certain orientation, the rupture that will be close to this biggest fault will be constrained. It means that if we look, it means that if the biggest rupture will constrain the smallest one, what we need to do to create a better pattern to create a better pattern of seismicity instead of considering an homogeneous one is to see the dependence between the highest magnitude, the highest magnitude with the lowest one. So what I'm trying to do basically now is to see. I'm trying to do like to see if, for example, I have some dependence between different magnitude bin. So what you can see here is so I did a box counting actually. So the black square are some historical earthquake of the lacular region. And if this is black, it means that there is at least one earthquake, and that happened in the past. And now what I will trying to do is to see if there is any dependence between, let's say, those magnitude 7. So we see that there is like 2 magnitude more than 7 that happened in the past, and see if there is like a dependence between the magnitude 7 and magnitude 6 and 7, for example, between 6 and 7, or magnitude between 5 and 6. So I will try to do some statistical analysis. And of course, because rupture are not only point sources, but they are more like they have a length. So we can also do this kind of analysis considering directly the finiteness of the rupture. So I also did some basic plot here just to show that if I have a rupture of finiteness, now I can consider I can see I can just take into account the finiteness of the rupture and not only the point sources, and I will try to see if there is any difference in the result that I will have when I will do the analysis, the statistical analysis, and yeah, to see if there is some difference between point sources and rupture length and finiteness of the rupture. So thank you.
Okay, thanks, Jarod. Questions? Anybody?
Maybe I do one just
Yes.
to
Go ahead.
understand. Maybe I missed something in this possible interaction things. You separated the magnitude classes, or
In
the
this
idea is
one?
also, yes, and also in the other one you show only between 6 and 7, the last slide.
Do you mean this
No,
one?
no,
Right?
no, the next one.
The next one?
No.
This one?
Yes. So this
This
is
one?
only between 6 and 7.
Yes, and oops. Okay, so it's okay. So in these two plots, okay. So in these two plots, I was, because for, let's say, for area sources, when we don't know if the orientation of the rupture, we will take like different orientation, because we will say that
Okay.
we have the same. We have a possibility to have a rupture with different orientation. So we will consider a different orientation for one earthquake, for one past earthquake. And what I did here is if there is if my historical earthquake is close to an existing fault, so it will take its characteristic. It means that if my historical quake will be, let's say, so let's say that this is an historical quake, and we have actually a fault that is nearby this historical quake. So instead of considering all the possibilities, so all the direction, here we just constrain the orientation of this quake by the fault that is closer to
Okay, now I understand
this one.
what you did. Okay.
And with this kind of things is we can do is when I will do the statistical analysis, probably the result will change when we consider these two things. So I just did some basic blocks here, but yeah.
Okay.
So, the results that you showed with the the Gutenberg Richter with the source, this one. So I mean, a problem, an issue with one source, but the others are okay. Is that right?
Yeah, only one source. Yeah.
Okay. So there's a bug, but the bug is source related. Yeah.
Yeah.
Okay.
Actually, yes.
Good luck. Okay. So any other questions for Gerard? All right. So thanks a lot again.
Thank you.
Now we can move on to Giulio's lecture. So Giulio, you can take the stage.
Okay. Okay.
So again, I mean, I think it's good for a lecturer to be interrupted by questions. So really don't hesitate. So I'm talking for you, Giulio, but I guess you prefer question than silence. So don't hesitate. If you need for some clarification or have a question that cannot wait. So just put on your mic and go ahead.
Okay. So I can start, correct?
Yes, correct.
Okay. So good evening. Today
Giulio,
talk.
we see the presenter view and not the
Yeah.
full screen.
So condividi. Can you see the screen?
It's the same. We have, yeah. Again, so yeah.
Interrupt. Okay. Try again. Okay. Condividi. And now what do you see? Can you see anything?
Again, we have the slides on the left column.
And if I do like this, can you see my screen?
Oh, okay, hold on. Again, that's back to the initial setup.
I think
Io
you need to
maybe
click.
in impostazioni di visualizzazione, there should be exactly the first one.
The first one. Oh, yeah.
Now?
Oh, yeah, perfect.
So you can see it now. Thank you so much.
Yeah. All right.
Yeah. Okay. Can you see my mouse? Just to be sure what I see.
Can you move it?
It's
Yeah,
on the
yeah, we can.
here on the blue. Okay.
Yeah.
Okay. So thank you for your patience and for your time. And today I will discuss with you about this seismic cycle in the presence of hot and pressurized fluids. This is something we are studying, I've been studying in the last 2-3 years between Padova and a bit at the National Institute of Geophysics here. I still work a lot with them, and especially with people from China, from the National Natural Science Foundation, which is actually granting to there is a Center of Excellence in Beijing. I better go to the next slide. And so in Beijing, especially with Lu Yao and Shangli Ma, because basically there are some machines installed worldwide to study friction and seismic sleep and the seismic cycle in the presence of hot and pressurized fluids. For sure, I think all of you know about the work Elizabeth is doing in Utrecht using one of these machines. But then we worked a lot with these people in China, and we have two very similar machines installed in Padova and in Beijing. So I work a lot with them. And the machines were designed by Toshi Shimamoto in this case. And so he really has a pivotal role. I don't know if any of you met him in the past. He's a great guy. And he retired from in Japan in about 12 years ago, but then he moved to China. He worked there for 10 years. In Japan, you have to retire when you're very young, at 62. And then he worked and developed many experimental machines. And I think the one I will talk with you today is quite of a jewel in that sense. It's quite a unique machine. But then we also work with people here in Padua, and especially with Wei Feng. He's a Chinese guy. He completed his PhD. I will show some of his results. And Wei Xin Wu, I will show some of her results today. But also Simone, now he's a postdoc at the University of Reno in Nevada. He's a structural geologist, and so you did more field work, like Rodrigo here, Gomila, which instead is working with us here in Padua, and Telemaco and Michele. They are professors now in Padua. Then there are people from IGV, but in this case, mainly the work is done by Chiara Cornelio, and she's an engineer as a background. And then with Alessandra Sciarla, Monica Piocchi with these strange eyes in this picture. And they are instead, Alessandra and Monica, they are geochemists and volcanologists. They work mainly the Osservatorio Vesuviano. So I'm talking about the Campi Flegrei area. We're also working on these materials, and maybe I will spend a few words. The other people are from Chile and from EPFL. I think I have this bloody, bar on the top of the face of Marie Violet. And so there's a lot of collaboration, and also especially with Annette Mortensen from Iceland. And in fact, we also worked on samples coming from the Krafla geothermal field, and I will discuss a bit here. And then Tom Mitchell and other people. These are people I work at mostly in the field, I would say, in some cases. But so I move on. So we'll describe a bit about fault friction and earthquakes in hot water. And so seismic cycle in hot water, and this will be the field case. That actually was a bit of inspiration for other studies we did in the last 7 years. And then frictional physical state of water, the case of Krafla in Iceland. And the conclusions. Yeah, the Bolfin Fault Zone is in the Atacama Desert in Chile. So regarding fault friction and earthquakes, what I define by friction here is simply the ratio of the shear stress versus divided by the normal stress, but then there is support pressure. And so this is basically my definition here of friction coefficient. I will include this factor, the Biot factor. I will give a value of 1 to make the story easy, but actually this guy is quite a strange guy, and this goes to pore elasticity and other properties of fault materials. And of course, a lot of seismicity occurs because of the interaction of the fault rock materials with fluids, and especially hot, because at seismogenic depth, when you go down at 10 kilometer deep, the ambient temperature is the order of easily of 200, 300 and more Celsius. But then if you move in geothermal fields or in volcanic areas, at that point you can have 300 Celsius, at 1 kilometer or 2 kilometer deep, so very shallow. And this is quite relevant. The interest, of course, is in geothermal energy, but also for the natural seismicity, like we have currently going on in the Friglean fields near Naples. Regarding the seismic cycle, of course, I really invite the young people to read the book by Harry Reid. This report, actually, he wrote in 1910, which is where he describes the elastic rebound model for the seismic cycle. And it's a beautiful piece of work and easy to read. And there are, and the nice thing of the elastic rebound model, where probably I think all of you are aware of, is based on the field observations, topographic observations. And in fact, basically there were topographic surveys done before and after the San Francisco earthquake. This part of North California was there was a very important project, topographic survey project, was performed in between, you see, in about 40 years. And at some point, Ernie Wright was involved at the very late in the early 90s of the 19th century. And then, of course, there was the big quake. So here, the red line segment is the San Andreas fault, and the scale. This comes from this book, from the report of Henry Wright, and it's showing here. This is 1 meter in the in the vertical axis. In the horizontal axis, we are talking about kilometers. Okay, so there is a factor of 1,000, and before the earthquake, just before of the topographic measurements, and they had, let's say, this kind of green curve. But then after the quake, there was the displacement associated with the seismic slip and so on. And of course, there was the displacement of these topographic stations and that and so on. So there was this clear evidence for this kind of elastic rebound, which actually he reproduced in his book by doing this simple analog model where he put a piece of jelly between 2 pieces of wood. So the scale is a couple of centimeters now, and then he shear it. He shear it, and then he observed, of course, the elastic distortion, and then eventually the seismic slip. So you really, if you think that this report was written more than 1 century ago, it's a beautiful piece of science that you can download this from the web. So the spring slider is something that reproduces this seismic cycle, because basically the idea is that there is the pool here in the case of the spring slider model, we have a motor installed in the bottom. Here would be in the bottom left, and it is pulling this wire, which wants to reproduce the far field, the velocity and loading of the spring. So this will be a sort of plate motion, and the spring are the rocks that are storing elastic strain energy, and then the spring is attached to this to the slider here. Okay. This is something we do with the students in Padua, and the blocks are sitting on the aluminum plate, and there is this sandpaper, and the contact here is the fault. Okay, so if you just, I hope it will go. So of course there is this far field loading, so the plate motion would reproduce. It was a force shock, and then you will see now the main shock for this case, okay? And then it is, and this excites the students, and we are monitoring the magnitude 9 for our case, and we are monitoring with this laser the elongation of the spring, so we can measure the elastic forces, and then there are the detectors in the background. Here they are measuring the movement of the slider. I think I can, yeah, I can down. Can you hear me? I don't know. Oh, yes. So this is the very simple, okay, process that is described of this kind of frictional instabilities that are described with the spring slider model, which is you can also describe it in a very simple way by using the equations of the harmonic damped oscillator. But this is something we did not discuss. These are the data we collected in our lab here with the students. So you can see here the elastic loading, so the elongation of the spring, and then the stress drop here. That means that the spring is shortening because the here below is the slider, which slides and is sliding during the seismic slip, simulated seismic slip event. And so you can see here a quite regular, of course, fixed slip, and which, as I told you, can be described in several ways. And this is something we do with the students. What is the maximum slip you can have in this because of the friction drop and so on. However, of course, the seismic cycle is quite complicated thing, as you well know. So this is these are the earthquakes and in the stars, and we can see the evolution of the fault strength with time. And when you have an earthquake, there should be, of course, a stress drop, a friction drop, and a decrease of friction. And at the same time, and then it's recovered in, during the seismic cycle between one earthquake and the next one. And at the same time, we have the evolution of the stresses until the fault will fail. And this is not regular at all. At the same time, when sleep happens, of course, when there is the friction drop, that means when you have the seismic event, there is most of the displacement at least in most faults accommodated. And then we have this stage, which is the interseismic stage between one and the next one. And maybe the sliding velocity is 0 or limited to a few nanometers per second, or that means could be maybe millimeters or less per year. And so on. We can also have some pre-sleep events, this or whatever, that, geodesy is showing such a fantastic image of all this and other techniques. What happens in this interseismic phase is, people try in the lab to discuss in terms of what people call fault frictional healing. That is an increase of the static friction with time. So these are the seminal studies of Dean Dietrich, where he was sliding two slabs of a rock made of quartz, a quartzite, and or westerly granite in other cases, and he was observing how this static friction was increasing with time. I don't describe in detail these kind of experiments, but this is what people usually see. This kind of interseismic thing in the lab can be very different from what happens really in nature. It's one aspect of friction. So static friction increases with time for many reasons, but another important reason, which is not described in these experiments, is sealing or the cementation of faults because of precipitation of minerals from fluids percolating in the fault. So this stage is quite peculiar. We try to describe it in terms in the lab, and this was a quite long experiment. I mean, 10 to the 5 is about 1 day of hold, 100,000 seconds. But you can even do it longer, as we did here in Padua, and you can go more and more up to 1 week, and you observe most cases this behavior, sometimes not. The other thing about friction, which I will discuss a bit, is the evolution during the seismic slip event. So when the rocks slid at an average speed of about 1 meter per second, and in this case, friction drops of a lot in some cases, at least in the lab. We observe a decay of friction with slip distance that can be of the order of 90%. So if initial friction is 0.8, because of this healing, let's say, whatever it is, and then you start to slid at 1 meter per second, in few tens of centimeters or less, sometimes millimeters, friction drops down from 0.8 to about 0.1 or less. For some rocks, even probably is negligible. I mean, it's almost 0. So we are measuring the friction of the machine. But now this is some aspect I will discuss mostly in this talk. But then we have, of course, the role of fluids in the seismic cycle. So this is an example from the Basel experiment, or the failed attempt to exploit an enhanced geothermal system in Basel in 2006. Failed because eventually at this depth of about 4.6 kilometers, by injecting water, even if at some point they stop in doing that, after a few hours they stop. Eventually they trigger at a magnitude 3.4, and basically the experiment failed, and they had to quit with this attempt to exploit and geothermal energy production in the case of Basel. But so clearly the injection of fluids has a pivotal role, as you well know, and clearly is mechanical, just because by increasing the pore pressure this in the fault or around, that will decrease the effective, the effect would be to decrease the effective stress, and this helps nucleation of earthquakes, but also chemical. And this is the kind of example of fluid rock interaction you can have in this case of 5-6 kilometers deep, when the wall rocks here were about 250-300 Celsius. So the starting rock is like this. It's a granite. Okay, to make it easy, it's a granitoid rock. The white is feldspar, and there's a glassy vitreous rock mineral here is called quartz. So you have quartz, feldspar, and there is biotite and other minerals. But then, because fluid rock interaction, it becomes this green material here, which is very common, quite common in the fault cores in this place in the Atacama Desert in Chile. And also you can see here the solidified friction melt. This is a pseudotachylite. So this is a rock that was produced during an earthquake. And there are also older ones around that also have been altered. So we have a physical role of water, of course, which is critical, but then also the chemical one. And this is also very important. You can have totally different mineral assemblages in fault zones. And they are very important in the healing and sealing processes. Because of this, there have been experiments for decades about friction and the role of water, especially in a temperature, and people use mainly triaxial machines. So these are the seminal papers by Lochner and Blampede in the 1986, 1991, and where they were using you can see here the rock spacement, 20 millimeters, they're quite small. And this is the experimental fault. And the experiments are done over a big range of temperatures. They range from ambient temperatures to about 700, I think 600 degrees here. I hope you can see this in the in the bottom right diagram. What I observe is these kind of transitions in friction. Basically, the sliding can be quite stable, and then, however, above a temperature here was only probably 70 Celsius, it start to be a sort of oscillatory slip. So this stick slip behavior here. I hope you can see it in the experiment 200 Celsius. So at room temperature, they don't observe these instabilities, but then they observe them at 150, 200, and even at 200 Celsius, there is something, 250 Celsius, something happening. But then when they hit at that point, these stabilities, they disappear. Clearly, there is something changing in the properties of the rock, in the stiffness of the machine, and other things. However, there is a range for temperatures where there is instability, which is in the presence of hot water in this case. And this is described, probably you know, by the Rayton state friction load. You heard about that, but I will not spend much time on this. But basically, maybe I can show in this diagram, it comes from the experiments that were done in Utrecht by several people, and now Elizabeth is doing something like this using calcite. In this case, they use a rotary machine, so they can slip the gas. In this case, are powders, and they can slip them for maybe 50 millimeters or more. So the previous experiments, they just stop at a few millimeters. They can expand this range, which is quite important to understand the role of strain localization process in these layers of powders, of rock powders. And here they show again this difference, A minus B, that basically wants to make the story very short. When A minus B is positive, it means that the resistance, the friction, increases with velocity, and this makes very difficult to have earthquakes. Basically, it's basically impossible to nucleate. However, when the the friction decreases. The friction decreases with increasing slip rate. You go in this what is called velocity weakening regime, where actually earthquake nucleation can occur. The very nice thing of these rotary machines is that first of all, you can really investigate, in this particular case, you can go easily at 500 Celsius and so on, but also the role of displacement, and also at quite large also stresses, effective stresses of the order of 200 megapascal and more. One of the points that really I was curious about by reading these papers and was also the role of water, the physical state of water. Water can be, of course, in supercritical state, could be liquid, could be gas, or let's call it steam. And this supercritical point happens, is at a temperature of about 374 Celsius and 22 megapascal. And this is clearly a very interesting condition for water that can be achieved in many environments, especially if you go deep and in what we call the green schist phase field, that's in petrology. Excuse me, so there is something weird here. I forgot to kill this. Now, excuse me. So the idea is to investigate what happens also if there are phase changes of water in the seismic cycle. And especially when you are in geothermal fields, it's interesting the transition from liquid to also from supercritical to liquid or from liquid to steam, just because of the pressurization. And this may be has some consequences in the seismic cycle in these environments, shallow environments. But if you go deeper, at that point, the transition from supercritical to liquid also may have a role. And so there are also some geophysical investigation and that may suggest that something is going on when there are these transitions. This comes from the geothermal field of Lardarello Travale. This is probably one of the largest geothermal fields or is the largest in Europe. They produce about almost 1 gigawatt of electric power in this area. And so there is quite a lot of seismicity going on, which is quite shallow. And there have been several studies. This is one published by Gostinetti et al., where they discussing, this is depth, goes down to about 20 kilometers. And you can see this seismicity, the crosses are the hypocenters in the Lardarello area, which is this diagram to the bottom left. And then they have these anomalies, or let's say this is I just put these waves here, and there is a sharp decrease, probably at about 10 kilometers deep, and this is related to they think to the most recent igneous intrusion at this depth of about 10 kilometers. And on the top of it, they think that there is a particular horizon called K horizon, which is attributed, this kind of transition, which is attributed to the presence of supercritical fluids, and most of seismicity is on the top of it. We can discuss now if it's the transition from supercritical to steam or supercritical to liquid, or is at what we call, geologists call as the brittle ductile transition in rocks. However, it's quite curious that you have these kind of transitions, especially on the top of, most earthquakes nucleate above this. So this seems to suggest that there is some relation between seismicity and phase transitions. So this is just to keep in mind. I will move now to the field case and the seismic cycle in hot water. And this we are in the Atacama Desert in Chile. And of course, we went there because the faults that are green in color here, these are drone images we collected and used for the field geology survey. So you can follow these alteration zones. These are the fault cores of faults that sometimes, like this, in this case, actually they strike for 50 to 60 kilometers. So we are, you see, to the left, This is the coast of Chile, and we are just south of the town of Antofagasta. So we studied these fault segments here, and the rocks have been they got this green color in a range of temperatures between 270 and 420 Celsius at 4-6 kilometers deep, and about 110 million years ago. And they are cutting this crystalline basement south of Antofagasta. And when you look at the outcrops, so this is the Playa Escondida, where we worked for a while. Now I'm showing you these are a drone image that use a support to map the faults. The scale you can see here is only 6 meters. And there are rocks coming here from the right, which are not altered. It's the host rock. So you as I told you before, and this is what we call in jargon fresh. It's a fresh rock. However, when you move in these fault strands, the rock becomes green, and there are these pseudotachelites. So there is evidence of seismic faulting. The age probably of this seismic faulting is about 110 million, 112 million years ago. These are pseudotachelites. I mean, I don't want to spend too much time here, but there are multiple generations. And then, yes, we can discuss, but we are about this range between 4 and 6, 4 and 8 kilometers deep. The rock was already altered when the pseudotachelite was produced. So this frictional melting occurred in an altered rock, and perhaps there was free water. We don't know that. For sure, there was a lot of water in the altered rock. Compared to the starting rock, which was quite dry, there was already a strong fluid rock interaction. So what we did was to understand if you can produce frictional melts with these rocks and under which conditions. So we did several studies here. I don't want to spend too much time, but the point was I'm plotting here friction versus slip, and I didn't show you here the velocity we impose in these experiments was 3 meters per second. So this was basically seismic slip conditions. However, the temperature was only 25 Celsius. And these are the conditions we worked on. So we pressurize. There is a chamber here. The sample is installed inside the chamber. And there are dry and drain conditions.
Giulio, sorry, I think Menandrin has raised his hand. So
the main point is that friction decays, and also whatever conditions we studied in the presence of water was quite easy. Free water was easy to produce this artificial, in this case, pseudotachelite. So frictional melting occurred, and so there are glass, and these are images at the scanning electron microscope.
Okay, hold on, Giulio. Just let give a chance to Menandrin to ask his question, maybe, if that's okay with you.
Lost that completely.
Do you hear us, Giulio?
Yes, I can hear you.
Cool. Just a brief question on the pseudotachelite. So you said that there must have been a lot of water involved, but what is the evidence for that? What are the processes that must involve?
There was for sure water I mean, they are cutting rocks that have this green color, okay? And so there was fluid infiltration in the fault zone and interaction between the fluid and the rock. The initial rock is like this. It's a granodorite, and the minerals have, the only mineral has a bit of water is biotite, but then the other don't. I mean, there is about 2% of water in this rock, but then the rock became green, and now there is about 15% in weight of water because of the minerals, chlorite, epidote. So the rock interacted. The point is, if there was also free water, I mean, water in the pores, we don't know that. I don't know if I answered.
Yeah, you did. Cool. I like it how you got so used to talking to seismologists who don't know so much about rocks. You should say this is a green rock.
Yeah, you're right. Yeah, the color green is due to the formation of minerals that we call the chlorite, epidote. Now, epidote is a mineral which has about 3-4% in weight of water. Chlorite can have up to, I think, if I remember well, up to 12%, 50% in weight, and there is a lot. So the starting rock almost didn't have any water, granodorite here. But then there was this interaction. I mean, there was the ingression of fluids. And these fluids come from a bit from magmatic sources, but mainly from the surface. Just to tell you, we did isotopic studies and so on. And so this impregnated the mineral assemblage of water. I mean, new mineral formed. Because if these minerals here, like one is called feldspar. Or then there is another mineral that is called biotite, but especially feldspar. If there is water, it becomes unstable. It reacts to produce epidote, for instance. Okay, an epidote has water inside. This is quite crucial. I mean, it's fluid rock, an example of fluid rock interaction, and which is, and also the properties of this mineral can be very different. In the case of epidote and feldspar, the mechanical properties doesn't change much, but there are also other minerals that can form that are very weak, sort of clays, for instance. So you start from a strong mineral feldspar, it interacts with water and becomes a mica, a phyllosilicate, which has water inside and is also weak. I don't know if I'm confusing more.
No, this is perfect. This was very clear and useful additions. Thanks a lot.
Oh yeah, I'm sorry. Thank you for stopping me. So the point is this one. We don't know if there is water in the pores when seismic faulting occurred and produced the pseudotachylite. So we don't know this, but we know that the rock was already strongly altered. So I don't know if the water was just all attached was inside crystals, let's say, or was filling pores. What is interesting from this pseudotachylite, which is quite unique, is that I don't know if you can see they're full of vesicles, but and also big ones. So it looks like there was degassing, there were other processes going on in this melt, which is quite curious. It seems to suggest that there were free fluids, but these are just, so it's something we discuss in these papers. But we wanted to see if you can produce frictional melts when there is free water. So we did experiments in the presence of pressurized water in the lab, and we produce it quite very easily. So these are glass with Claston bubbles. I don't know if I don't see my mouse anymore. I don't know what they did.
Actually, you were back in the, okay, all right.
You see now?
Better. Now, yeah, it's better.
Okay, excuse me. Sorry.
I'll be back as well.
Yeah. Okay. So these are I saw the nobody I showed you before. I was discussing about this, the green color, the pseudotachylate here, and there are these white things here are, in some cases, they are elongated vesicles. That means that they are cavities, and then they were filled by minerals after the melt solidified. We call them amygdalae in geological jargon. But I think the point is that you can form frictional melts in the presence of pressurized water. And this is what we show in the experiments, where we pressurize the fault, and after a few centimeters of slip or less, there was already a melt layer. So this is the sample here. I put you can see here the red dot on the right. So we made a thin section, and you can see the artificial pseudotachylite. And you look at the electron microscope, and you are sure that it's glass, as you can see on the bottom right. So why I'm doing all this? The reason is, first of all, we have this field evidence, but the other thing is can this rock form? And even in the presence of pressurized water? And the answer seems yes, but this was done at room temperature. And then we installed this machine here in Padua, and there is the twin one in China. And we built this machine in order to do the experiment not at 20 Celsius at ambient temperature and then slid the rocks, but at 400 Celsius. So reproducing these deep conditions in terms of ambient temperature. And yeah, we installed this during COVID. And yeah, and this is the vessel. You can see now it's installed. And I just explain a couple of words, because this is so we have this is an example of these rotary machines where the rotation is imposed by a servo motor up here, and then there is this is a gear system, so you can choose the rotary speed over. We have about 1 billion, a range of 1 billion, which for samples that are about 28 millimeters, maybe there is here, okay, 28 millimeters in diameter, they correspond to slip rates, equivalent slip rates ranging from 50 centimeter per year to 2.0, 2.2 meter per second. So we cover with this gear system a huge range of slip rates. But then the trick for this rotary machine is that we have this vessel, and this was designed by Shimamoto, and it took 20 years of work for him. And it's not easy, because you have to slid the rock in the pressurized conditions. So this is already complicated because you have to confine it. And then there is a furnace. So this red box here is the furnace that can heat up the rock on the water inside the chamber, the vessel. The vessel is this gray stuff here, up to 500 Celsius. So there is also a cooling system. So you can see here our chiller. So this pumps cold water to cool down some parts of the machine, because you don't want, because of the temperature, to expand some metal parts. Otherwise, they will stick and you will break your machine and vessel. So it took a lot of time to make this work, and many attempts. And this is why I just bought it. I decided it was too complicated to design my own with other people here. So, and it's a great device. And to make the story short, I mean, this rotary configuration can allow you to have these slip rates for nanometer per second, so centimeters per year, plate motion, basically 2 meters per second, so seismic slip. And the slip is a rotary configuration, so you can slip as far as you wish, depending on the rock and the wear rates, how you break the rock, basically. The other point is you have this range of conditions from 20 to 470, 500 Celsius. So, and also the pressure are between atmospheric pressure to 70 megapascal. 70 megapascal per pressure, so we're talking about 7 kilometers deep in hydrostatic conditions. And the point is that we can investigate what happens in the transitions from liquid to supercritical. So we cover this range, or from vapor or steam to liquid and supercritical. So these are now experiments, again, reproducing seismic slip conditions. So here the velocity imposed was of 1 meter per second. So you can see here in this bronze color to the right, the velocity function. So we impose this velocity function and the rock is slid for 3 meters. This is wrong, not millimeters, is meters. And the friction evolves from about 0.6, a typical value, and drops down to 0.2. This is for rocks where there was also frictional melting. And the pore pressure was quite high. But look at the temperature from 30 to 400 Celsius. This is ambient temperature. I think the main message here is that whatever the ambient temperature is, and this is, I think, is quite useful for modelers. You have always this kind of decay, and there are small differences here. So what we see at 30 Celsius, really, you can also apply to 400 Celsius. There are details which matter, but to make the story short, I think you can use the same sleep weakening law in numerical models of seismic sleep to make the story for rupture dynamics. I think modeling is a good thing. And this was, as I told you, 25 Celsius, the experiments we did in Rome in the past. So it looks like there is this decay. There are some slight differences, but I think the crucial point is this one: rapid ecoseismic friction decay, independent of ambient temperature. Then the kind of process here where maybe there is some pressurization of the fluid and other things, but surely there is melting, because after the experiment, you recover the rocks here. This is the experimental fault I'm showing here the mouse on the top right. And when you look at the scanning electron microscope, now the scale is 4 microns. This is the solidified melt layer, and there is all these tiny crystals that were produced during cooling of the melt. So this is a typical, what we call pseudotachyle. Yeah, I don't want to go too much long, so I will discuss a bit here slide-on-slide experiments. So this is about friction in the presence of hot and pressurized fluids, basically during earthquakes. Basically, there are no differences. We also have data now with other rocks, and we always observe this behavior, other rock types, not only rocks that melt, but also rocks that carbonates that are more interesting from the Apennines, for instance. But let's move on to the slide-on-slide experiments on fault healing. So as I told you at the beginning, this is what we know about static friction that increases with the contact time, or what people call hold. So what we do in the lab is to slide or slip, for instance, at 10 micron per second. And so this is friction, and maybe it's about 0.75, like here. And then there is this hold. So we stop the two rocks and keep them in contact under the same normal stress for some time. In this case, the hold lasted 300 seconds. So, and there is this relaxation of the experimental fault, but also of the machine. And in this case, it lasted 300 seconds. And then you start again. So you impose again a velocity of 10 microns. And so you have this abrupt increase in friction in this case. And here the increase was about 0.05. So in this diagram to the right, we are plotting hold after hold, increasing time holds. Here was 3 seconds, then after 10 seconds, and this dashed square is this example, so after 300 seconds, and so on. And what people typically observe, like in this experiment at room temperature, is this increase of static friction with the log time. So this is the Dietrich type, is described in this way. Then other people did it with quartz in this case, but so it was the the behavior is similar, but here the experiments were performed in a vessel at temperatures between 100 to 100 Celsius. And excuse me, I see this, but I was never able to kill this kind of stuff in all my classes. I'm a disaster. Let's move it somewhere. I don't know how you killed that. I forgot how to kill it. In any case, you observe this increase of the static friction with time and temperature again. And people think is due to two properties, two processes, excuse me. One is the kind of bonds that form between the asperities. Now the scale is 200 microns here, so the upper block and lower block, and with the time, there are bonds forming. So people call this quality of the contacts, quality of the asperity. So the quality increases. There are better bonds, stronger bonds with time. And so more you stay there, more you put in contact, and higher will be the static friction. However, there is also another process going on, which is very important, is that if the two blocks are under load, the real area of contact will increase. And this is a beautiful case, where in the bottom right. It is a very famous paper by Dietrich and Kilgore, 1994, where they put in contact two pieces of plastic, basically, and they were observing how the area of contact, real area of contact between the two surfaces was increasing with time. So after 1 second is in red, after 100 seconds is in, you can see the yellow, and so these asperities start to connect to each other, for instance. And then if you wait for 10,000 seconds, the area increases and increases. So this increases the real area of contact, and this makes also the static friction higher. So there are two processes going on. What we call this real area of contact increase, but also which makes the friction higher, static friction higher, because you have to break these bonds, these bigger asperities. But then also the bonds, the quality of the bonds can evolve. And this is not much discussed, actually. So the quality, I mean, the kind of bonds, hydrogen bonds, van der Waals forces on bonds, precipitation of new minerals in some cases, especially when you work in temperature. So we worked with these rocks again from the Atacama Desert and from Chile. And this is how they behave, this what we call this frictional healing. So this kind of increase of friction after one hold during this period. And not surprisingly, we observe this behavior. So and this is for the green rocks, the rocks that already interacted with water a lot in nature. Okay, we make powders of this rock, and the holes go up to 300,000 seconds here. So basically, it's a very long time. I mean, it's 5 days. However, when you deal with the white rock, the behavior is very different. You observe that after between 10,000 seconds or more, friction starts to decrease. I mean, the static friction decreases. And so basically static friction, the rock become weaker, the fault become weaker. Now, why this happens? I mean, this is quite curious. And it was published a paper in 2023 by Jepson, by the group of Lochner at Menlo Park. And they observed this in granite. They start to say, so a fresh, let's say a rock that never interacted without fluids, a fresh rock, what we say in jargon. And we also did, we studied with electron microscope this lip zone, if there were really chemical changes. They're very tiny. We look at the surface after the experiment here with several techniques. So here we use the micro-Raman. These are techniques to find if there are new minerals forming. I don't want to spend too much time, but actually there were new minerals forming, especially after the very long holes. So this is a cabasite, is a kind of zeolite. It's a weak mineral actually forming. So it looks like there is something going on that makes the rock weaker. So it's sort of the quality of the bonds that is decreasing just because of the formation of new minerals. But then there are other processes that probably are occurring important that we cannot detect. I mean, we have a feeling that is something important going on, because we also do chemical analysis of the fluids after the experiments. So this is something we are trying to understand more and more. What is the impact of this? Well, this is just an example that if you have, the fault strength at some point start to decrease because of this process. For instance, given the same loading rates, the seismic cycle will be affected. This kind of stuff can occur in enhanced geothermal system. I mean, if people want to hydrofrac at depth, and the starting rock is a fresh granite or whatever, they really can change the properties, the frictional properties, and this can have an impact on the seismic cycle, just because of the lower static friction, let's say, that is, I want to show in this case in a very simple way. I think I will talk about this and then I close because I'm going longer.
Yeah, hold on just because it's late, so I don't know how long it will take.
Okay, but I can also stop here.
No, it's I don't know how long it will take you. That's a
No, well, this case in Iceland, okay, I show a couple of slides and
Yeah.
okay.
Cool.
This is something, the frictional physical state of water here. We are in Krafla. Krafla is in the north of Iceland, and so just okay, go. And this is just to give an idea of how this is the geothermal field in Krafla, and this is the power, the geothermal power center, and to the north there are also what we call the lava flows of the Krafla fires. It was an eruption in 1975, and yeah, this is a power plant that produces about 60 megawatts, so quite smaller compared to the Italian one of Lardarello I told you before. And they of course extract here. You can see so these are this is the steam that comes from, in this case, I think from about 2 kilometers deep. And there are at least 44 active boreholes. They go between 1 kilometer and 3 kilometers deep. And so it looks like, earthquakes are due to earth imprisoned in the cavities located within the earth interiors. I mean, there's a lot of seismicity going on. And like Aristotle's model was about, earthquakes produced by these winds, deep winds. I think it was playing with volcanoes. I mean, if you go in volcanoes, you feel the shaking, you see all the steam and other gases coming out. So probably that was his consideration. And it's interesting here. So this is it's about 2 kilometers to 3 kilometers per about about 4 kilometers. So this is the map view in this left side. The power plant is here in the bottom, and you can see the head of the boreholes, and then they go deep. Sometimes they go oblique, other times they go vertical. And you can see the depth they reach is about in some cases they go down to 3 kilometers deep. And these are the epicenters and hypocenters reported. Most of the seismicity occurs again at only 1.7 kilometer at depth. This is below sea level, and this is the geothermal gradient. There is a lot of seismicity between 350 and 400 Celsius. So we are just, if it remain to the fluids, we are just in the range of supercritical fluids to liquid, or if you decrease the pore pressure, that can be also steam. So some seismicity can be due to these kind of water liquid transitions. These are the rocks, the powders used in this particular case, which is one kind at the moment. Actually, this is one I discussed here. And these are the experimental conditions. So experiment liquid and then vapor and the supercritical conditions. So at some point you have to change the pressure in order to go in supercritical conditions. What is important is this diagram probably, which shows you the experiments in vapor versus experiments of water is in liquid conditions or supercritical, and you can observe the frictional instabilities. So it's important to say that the machine properties don't change. The stiffness remains the same. What is changing is the friction properties of this material, just because of the transition liquid to vapor or supercritical, or also because the temperature increase. So I'm plotting here the reference friction, by the way, is higher when you are in vapor condition. We also did other experiments not shown here, playing with vapor at lower temperature, but still at the same effective stress of 10 megapascal. But you can see that liquid is low and vapor is a bit different, as you can appreciate here. And also this frictional healing that we discussed before is much stronger with increasing temperature, much higher in these rocks. And then I think it goes to the stress drop, which are something we are really interested in. And we observe in many other rocks now that basically increases with when you are in vapor state. In vapor state, the machine is much more, I mean, our experimental fault is much more unstable than in other conditions. Yeah, I think I can really quit here. I mean, the message was about mainly about these kind of considerations about the role of given the same effective stress. So the normal load, let's say, is the same minus the pore pressure. However, we can observe these huge differences by just changing the physical state of the fluid. And this has some relation with the seismicity observed in Krafla, for instance. But I don't want to spend too much time. So I skip this, and then I go to the end. Just to say that seismicity is driven by hot and pressurized fluids, as you well know. And the important point that high-speed seismic slip rates friction is independent of fluid temperature and pressure. So doing experiments also at ambient temperature or 400 Celsius looks like doesn't change much, which is quite important for making a general law for friction during earthquakes. Instead, the sub-seismic slip rates are differences. And these are the one I basically discussed a bit with you. I think, yeah, natural force might be more stable in presence of vapor, and I think I quit here. So sorry for the long thing. Yeah, I think I spent 1 hour.
Yeah, that's perfect. Thanks a lot, Giulio. Very impressive. A lot of results.
And
Yeah, a lot of science. Okay, questions? Anybody? Okay. Well, I can start with one just to break the ice. It's kind of counterintuitive that, you know, if you higher the pressure, I mean, the dynamic friction doesn't change that much. You would expect, you know, some kind of, I don't know, lubrication or, you know, some effect. So you mentioned it's basically the same. It's not as, you know, one would expect, I would guess. What do you make of this?
no, I think that yeah, you are right. What in all these experiments what we increased was the ambient temperature when we reproduce seismic slip in the lab. And we kept the effective stress was always quite low. I mean, in the range of 50 megapascal, 60 megapascal. And then we used mainly solid rocks. We still need to play with gouges. This is something we'll do in the very next future. And there could be differences. So the role of pressure is not fully investigated. The role of ambient temperature, yes. If you increase the effective stress, you would expect any process to be triggered faster if just because the pressure helps to increase faster the temperature in the slip zone. I mean, the stress, I mean. So thermal pressurization, that kind of stuff maybe is easier to trigger, I don't know. But what is missing is the role of normal stress. I mean, at the moment, we stop in the experiment at about 50 effective normal stress. Yeah. So that's, but the general behavior, yes, I stop.
Okay, yeah, there's a question by either Alexander or Elizabeth, I don't know.
It's by me.
Oh,
I have a bit of a general question. You showed these very consistent results that at seismic slip velocities, the friction coefficient really drops by a lot, like 90%, you say, in that order. And it's of course due to all these effects with melting and all that. So what I wonder is, from a modeling perspective, if these are not considered, so your friction drop is a lot less. So let's say a drop to, in my case, it's to 0.35, and you don't have this at seismic velocities, this very strong drop. What does that mean? Like, what are the implications of not considering all these effects, all these processes?
Yeah, the first point is that I mean, you're saying that you have in terms of friction, you say that by simulating seismic slip, you have 0.35.
Yeah, I use rate and state friction, and with my parameters, like at seismic slip velocities, it goes to 0.35 as about.
Yeah, but this is, I think it's reasonable. I mean, we are considering here a flat fault, an infinite flat fault, and we are studying, I mean, our experimental configuration is reproducing an infinite flat fault. What happens in a small area of few square centimeters of this infinite flat fault? And roughness matters a lot. And so this is something is controlling. I think in geometry controls everything in earthquakes, and so that can really increase the dynamic friction during earthquakes. So probably the friction would go very low, but then because of the roughness. That matters. That matters. I mean, a lot of energy is also dissipated in this fracturing process and other processes. And without that, also in an infinite flat fault, you even don't have maybe seismic radiation because you need the roughness to accelerate and decelerate, the rupture speed, and so the ability to emit waves. So this is but studying the role of roughness in these experiments is very complicated because we explode the sample immediately. We are not able to confine it. So I wouldn't be concerned if you get 0.35. I think is great. Even though the processes are very different, maybe.
Okay, so it's essentially a matter of scaling. Locally, it will go a lot lower, but because of roughness over larger sizes, it will.
Yeah. And then also the other point is that we are applying some. I show here, but in other papers we did in other experiments, we studied velocity functions that are more related to elastodynamics. What people call the Ioffe function, this kind of stuff. At that point, of course, friction goes up and down because it's just in antiphase with the velocity. So velocity goes up, friction goes down, then the acceleration of friction goes up immediately. And at the end, the average could be 0.4, 0.5, and it just because of the slip pools. So this is another aspect that is not included in the experiments I show you today.
Okay, thank you.
Yeah. Thank you so much, Alexander.
You have a related question. So if you do have, 0.35 or 0.40 at seismogenic depths with a lot of compressive stresses, wouldn't you then expect that you generate a lot of pseudotachyllites and melts? Yet, if we go through the Alps and look at faults or in California or somewhere, I mean, you show beautiful examples, but it's not quite as prevalent, right? There's a lot of faults that we know had a lot of slip, but no melt evidence.
Yeah, at the moment, these high-speed experiments were performed on solid cylinders, and so you get these things, so you weld them quite easily. I mean, these are originally they were like that. Okay, these are too solid. These were done with the Shiva, the machine in Rome. So we slit them, and then the result is the welding and the pseudotachylite, as you said. However, there are two observations. I mean, the first one, we want to do now experiments with powders. So it's quite complicated to do them, but we want to play with powders. So put them at 300 Celsius, pressurize water, gouge, and shear it. So we have everything ready now to do it. I think we'll do it next month here in Padua. They are very challenging to do. We don't know what will happen. And maybe friction will just remain low. And so there is no reason to melt the rock. So this is one thing. But the other thing, I think the pseudotachyllites are hugely overlooked. And one of the reasons is that, so we are preparing a work there, is that ambient temperature matters a lot in producing also the typical structures that geologists attribute to pseudotachyllites. I mean, if you produce if the ambient temperature is 150 Celsius, for instance, and is very difficult to produce the small crystals tiny crystal typical of pseudotachylides that we recognize. So you will produce a sort of black layer, black thing that can be easily attributed to another. It's just a, I don't know if you understand what I mean. To produce the typical features of pseudotachylides, it looks like that we recognize easily. You need some ambient conditions, some conditions. And the other point is that they're easily lost from geological record, in some cases, just because of these alteration processes. So I wouldn't really, I mean, to tell you, I remember talking with, was with Nadia Lapusta. She was, oh, they're rare. And she was sitting on a rock made of pseudotachylides in Caltech. I told her, but you're just on the sitting on a rock that come from the Sierras in California. So the answer is we should expect the answer I think is that probably they're more common than we usually think. But it's also difficult to find them because they're not easy to preserve, and also sometimes they don't produce the typical features we attribute to pseudotachylides. So we just, oh, this is a Cardacasite, that's it. Maybe it's not. And the third one is that we don't know what happens with powders. Fluids and powders. Maybe thermal pressurization maybe is just the king of everything there. So if you have a powder, and it's more easy to have this, and you don't have high temperatures. Sorry, you better stop me because my brain is
Okay,
totally.
all right.
I don't
So
listen.
maybe another question, or I don't know if it's a quick one or not for you, Giulio. I wonder what a supercritical fluid will involve in terms of fault dynamics as compared to just water or liquid or gas. What is your insight for this?
Well, the compressibility is something quite low. The viscosity also, so it's compared to liquid. So it's quite tricky. It's quite tricky. We just, but also so studying the physical part is one part of the story. And the other point is that the chemical properties of water in supercritical conditions are very different. The pH is different. This matters in the healing phase, in this kind of, it's totally different. Just because, I don't know if you're familiar with cations and anions in water, but usually they develop in liquid water what we call the double layer. So basically there is an anion and then the molecule around, and they make a double layer. And then when they interact with a cation, there is this double layer in the middle. And in supercritical, just because of the properties of this liquid, of this fluid, excuse me, there isn't. So the reactions can be faster. Then the pH is lower and other things typically lower. So it's something to be understood much more. For sure, I think they impact a lot in the healing phase. That I'm quite, because we see this in the lab. And also the oxidation state, a lot of stuff going on. And also here we need to go toward what we call molecular dynamics model. So we are working a bit on that too. And that means molecular dynamics, these are experiments at the molecular simulations at the atomic scale, where people, physicists, and mainly material scientists, they can reproduce the compounds they are producing in picoseconds, or how do they evolve for a short time. And because also in our experiments, we do the experiment for 100 Celsius, then we wait 3 hours to recover the powder and the gouge, but to cool down from 400 to room temperature. But we lose a lot of information during this cooling. So I think the direction.
All right. Maybe a last question by Manandrin.
Yeah, just very briefly, going back to what you said earlier with the powder, you have lower friction. And I noticed this in your whole time experiment results. Is this always the case? Can you not get higher friction with powders?
So sorry. So is the friction is higher with the powders?
So I was surprised when you showed the whole time experiment, your coefficient of friction was with low hold time. It always started out very close to zero.
That's excuse me, is the increase. So the increase, I mean, the reference friction was about 0.7, and then after, when there was a hold and you start again, after 10 seconds, it increased maybe at 0.72. Then if you wait 5 days, it goes to 0.76. So it's
I
a
see.
delta.
So but that means that the presence of gouge or any powdery material cannot be the reason why faults have low friction.
Well, that's a. I think people usually think that the low friction in fault can be due to two aspects. One could be the hyperpressure. The other one could be the frictional properties of particular minerals like clays, phyllosilicates that have. If you have talc, for instance, that has a friction of 0.1, as far as I remember, 0.15, compared to a powder made of, of quartz, that friction would be 0.75. So the mineralogy matters to make. So it depends on the composition of the gouge. That changes a lot. And also the structure of the gouge. That matters a lot. I mean, if you needed to develop a continuous layer of these phyllosilicates, we call them, of these weak minerals, at that point the fault will become very weak. In the case of the San Andreas, they claim that there was the presence of this saponite. I don't know if you remember the work by Lochner and published in Nature after Sappho. I mean, they studied these gouges coming from the fault core, where they drilled at 2.5 kilometer deep, 2.7, and they found saponite. Saponite is the soap. In Italian, sapone is soap. So it's the soap. However, saponite, this mineral, is extremely weak, but is stable until 150 Celsius. Then it breaks down. If you heat up, it breaks down. So you need to explain the weakness of the San Andreas, you need a depth. Cannot be saponite. Probably maybe talc. I don't know, or could be the pore pressure thing that Jim Rice and many others discussed.
Okay.
So
okay. Maybe we can stop now, Giulio, because it's going to be late. It's nearly 6 o'clock.
Yeah.
Thanks a lot. Big round of
Thank you to you all.
Sorry,
I was a bit lost today. I must say, it was a long day of classes and other things. So, okay.
Yeah.
Ciao.
Thanks
Ciao.
a lot.
Thank you, Giulio.
Thank you.
Thank you.
See
a lot.
you. See you all. Ciao. It was great to see you.
Bye.
Oh,
Bye. Ciao.